Hello, and welcome to our program, Astronomy for Everyone. The topic for this month's show is the James Webb Space Telescope, and we're going to learn how it has transformed our understanding of the universe. And here to tell us all about it is our guest, Tim Campbell. Tim, welcome to the show.
Thank you for having me.
Oh, as always, as always. So, the James Webb, how is it different than the Hubble?
Than the Hubble. I get that question a lot, Don. So we have a number of space telescopes that we've launched over the years, and the Hubble is probably the most famous because of the breathtaking science that it was able to do, also the beautiful pictures. And when you look at pictures produced by the James Webb, you don't initially notice how different they are until you take a closer look. The James Webb is able to do things. It was launched to do things that Hubble simply cannot do. So there's a lot of groundbreaking features inside the Webb. But the main feature of it is that it is an infrared telescope, and the Hubble is a visual wavelength telescope. So we'll get into that a little bit as we get into it. So let's talk a little bit, I suppose, about how the telescope works.
Exactly.
All right. Okay. So with that, so I have an image for you, just to give you an image of the James Webb. Now, first of all, for size comparison, the Hubble is about the size of a school bus. The Webb is about the size of a tennis court. So it's a considerably larger telescope than the Hubble was. And you can see in the image that we've got these foil shields at the bottom of the telescope. Those are actually heat shields designed to block the telescope from the heat of the sun. This is an infrared telescope. Infrared is heat. And so if sunlight was able to actually hit the operating parts of the telescope, the business end of it, it would warm up and all it would see is itself. It would just have heat scattering all over the place. So we have to make sure that can't happen, and that's the purpose behind those heat shields. The telescope cannot point independently of the heat shields. So the configuration that you see, that's how it is in space. And we can never allow it to point toward the sun, nor can we allow it to point away from the sun, because if it pointed away from the sun would hit the backside and it would still heat up. So it's always pointing in the direction either forward in the orbit or behind in the orbit or up or down, but never toward the sun or away from the sun. If it wants to see something in the direction of the sun, we have to wait 3 months for it to go around the solar system with Earth, so that now it can safely point in that direction without having to look at the sun.
Okay, I see.
Yep. On the bottom of it, we have some of the operations parts of it, the solar panels. There's radio antennas and things like that down there, so it can transmit its data back to Earth, and that's how we talk to it. I will give you this image here. This is for scale comparison. So we have a human for scale on the left, and we have the diameter of Hubble, so that's a 2.4 meter mirror on that. And we have a 6.6 meter mirror on the Webb, but that's actually a multi-segmented mirror. So it's 18 individual segments. If you were to count the hexagons, you'd see that there's 19. That's because the middle segment, there's no mirror there. That's where the sensors
The light passes through to the sensors.
That's where it passes through. So, but there are 18 hexagonal shaped sections that are actually being used. And we need it to be bigger because infrared wavelengths are longer than visual light wavelengths. And so because of that key difference with the telescope, if it was only the same size, you would get fewer wavelengths across the aperture of the telescope. You would actually get lower resolution as a consequence of doing that. So I'll talk a little bit about the instruments. There are 4 key instruments that we'll talk about a bit in the show, and I will see if I can show them to you. So the first one is this guy here called the NIRCam. NIRCam is the near infrared camera, and so it's imaging photographs, but in near infrared wavelength light.
Is it overlapping a little bit of what Hubble does?
It does actually overlap a little bit of what Hubble does, but it goes quite a bit deeper beyond what Hubble can do, even on the NIRCam side. There's also another instrument that we call MIRI. MIRI is the mid-infrared imager. You would think it would be called MIRCam and NIRCam for, because then they would have names that sort of match the same pattern. Developed by different agencies, so they get different names. But it's essentially another visual camera but it's imaging in a deeper part of the infrared spectra than NIRCam is able to do. There's two more instruments of interest to us. The next one is this instrument up here called NIRSpec. NIRSpec is the near infrared spectrograph. This is one of the groundbreaking first of its kind features of the telescope, of any telescope, is that if you took a telescope like Hubble and you take, say, the Hubble, the famous Hubble Deep Field, I'm sure you've seen that image, and there are thousands of galaxies in this image, and you're trying to figure out, of all these galaxies, which one is the farthest. Well, you would have to measure the redshift of each galaxy one at a time, because the spectrograph on Hubble just picks up the spectra of one thing, the object of interest that you care about. So this has a microshutter array, and it's essentially able to take the spectra of lots and lots of things in the image, so that essentially you get the spectra of everything that showed up in your image all at once. This really makes short work of trying to figure out which thing is the farthest, if you're trying to do something like that.
Okay.
And then the last one is this really cool thing, FGS/NIRIS. So FGS stands for the Fine Guidance Sensor. We won't talk about that. But NIRIS is the Near Infrared Imaging Slitless Spectrograph. This spectrograph is another first of its kind. It can only do the spectra of one thing at a time, so it's not a microshutter array like the other one, except the level of sensitivity on this spectrograph is able to detect molecules in planetary atmospheres or in nebula clouds that are in space down to the parts per million level of sensitivity. So that is really cool. So we can not only detect if there's an exoplanet we want to study, we can tell you what the atmosphere is made out of. Which is really cool. No other telescope has been able to do that in the way that the Webb can do. So that's the instruments that we've sort of covered. We do have, I did want to show you this image, a different view, and we have these struts that are in the image. And the struts are supporting a secondary mirror out in front. So the light hits the primary mirror, that's the 18 segments, bounces off of those toward the secondary mirror. The secondary mirror bounces off of again, and it goes back through that cone that you see in the center and into the imagers. And that's where the sensors pick up everything. But there is a consequence of having these hexagonal segments. And that is that when you have a star, you get these things that we call diffraction spikes. Every edge that's detected in the field of view in the imaging train of the telescope is going to create a spike. And I'll go ahead and overlay this so you can kind of see what's going on. So there's the 18 segments. And you'll notice that the spikes pass precisely perpendicular to the edges of each of the mirror cells in the telescope. So when you see an image produced by the Webb and you see these spikes, probably it's because those spikes were caused by a star in the image. There are a couple of exceptions I'll point out as we go along. So those stars are things in our galaxy. Most of the images that I'll show you, well, maybe not most, but quite a number of them will be deep field images, images with thousands of galaxies in them. And so if you happen to see these spikes show up in those deep field images, you know that that's actually a star in our galaxy that just happened to be in the way. Of the deep field.
In our field of view as we're looking out into the universe.
Yes. Okay, so that's a little bit about how the telescope works. Let's talk a little bit about where it is. So this image, so it's super important to point out this is not to scale. So I've called that out in the corner of I have a message there that says it's not to scale. Earth orbits the sun about 93 million miles away from the sun. Webb is about 1 million miles farther away. It's actually 960,000 miles, but we can just round it off and call it 1 million. If you look at this image, it looks like Earth is halfway between the Webb and the sun. It's not, but if I jammed the Earth all the way to where Webb is, it would be a little bit cluttered. So there is a very important reason why it needs to be at that location. So first of all, Webb doesn't orbit the Earth. Hubble orbits the Earth. Webb is actually orbiting the sun. There's a problem with doing that, however. So if you think about the orbits of the planets, Mercury is the closest planet. It has an orbit about 88 days. Venus is about 224 days, I think. It's a little bit farther. Earth is 365. Mars is farther. It's closer to 2 years. Jupiter is about 12 years. Saturn is about 30 years, and so on. So the farther you are from the sun, the longer it takes to do a lap around the sun. This is a problem for the Webb because if the Webb has to be farther from the Earth and it's in orbit around the Sun, it should take longer to complete an orbit, and that means that it will fall behind the Earth. It will not keep up with us. But there is a magic that happens at the special location in space where we've parked the Webb, because it is precisely in line with both the Sun and the Earth, and so it feels the tug of gravity from both objects at the same time. And so if you sort of add that up, it sort of creates the illusion that the Sun is a slightly bigger star than it actually is, and that means that it needs to go a tiny bit faster to have a stable orbit around the Sun. And at that magical distance, the tiny bit faster happens to be a complete orbit in 365 days, just like Earth. So that's why we had to park it at that point. It's there again so that it's always shielding from the Sun's heat and also shielding from the Earth's heat at the same time. If it was in orbit around the Earth, we wouldn't be able to do that.
So that's one of those Lagrange points?
That's a Lagrange point, yes.
Okay.
That's the technical term for it. There are several of them. That happens to be one of them.
This has been an interesting first part of our conversation. We're going to have to take a quick break right here. If you have any questions, please send us an email. The address is down at the bottom of your screen. And coming up next is Term of the Month with Stephen.
Thanks, Don. The term of the month is transmission spectroscopy. Most of the nearly 6,000 exoplanets that have been found so far were found using the transit method. The parent star's light is monitored. A dip in the brightness can indicate that there is a planet passing in front of the star. The longer the dip, the bigger the planet. With the orbital time and the mass of the star, the size of the planet can be figured out. We can't see the planet, but if the planet has an atmosphere, then the spectrum changes when it passes in front of the star. This is called transmission spectroscopy. From this, we can tell what's in the planet's atmosphere. Exoplanet L98-59d was discovered in 2019 with NASA's TESS Space Telescope. It's about 1.5 times the size of the Earth and 35 light years away. Using the James Webb Space Telescope, transmission spectroscopy data suggests that sulfur dioxide and hydrogen sulfide are present. Conditions on L98-59d may include a molten or a volcanic surface. Additional observations will be needed for confirmation. If it is confirmed, then this is the smallest exoplanet that has an atmosphere detected so far. Volcanism could be driven by tidal heating, as on Jupiter's moon Io, but the planet's distance from the star is small, so high surface temperatures are likely. A year there is 7.5 Earth days. And that's the term of the month, transmission spectroscopy. Back to you, Don.
Thanks, Stephen. We're back to continue our conversation about the James Webb Space Telescope. So Tim, please continue.
All right. So we talked a little bit about the telescope, where it is, why it's in that place in orbit, the instruments on it. Let's talk a little bit about why we use infrared light. So I have an image for you where I'm showing sort of these really distant galaxies on the far right of your screen and the Earth and the Webb on the far left of your screen. And the problem is, as you know, the universe is getting bigger. And that means that the space between us and the distant universe is always expanding. And these galaxies that are occupying that space are sort of getting carried along for the ride.
This is sort of the raisin bread theory of the universe?
Yes, the idea that it's always expanding. So when the source of light is moving away from you, the wavelength of light that we receive is stretched versus the wavelength of light that was emitted at the source object. Everybody has experienced this in their everyday life. If you've been near a railroad and the train is coming by and it's blowing its whistle, and as it's approaching you, you hear the whistle at one pitch, and as it passes you, you hear that pitch bend and drop to a slightly lower pitch. That's called Doppler shift. And so it's a higher pitch because the source of the sound is coming toward you, and it's a lower pitch when the source of the sound is going away from you. This is the same thing that we're doing with the distant universe, except we're talking about light instead of sound waves. So The distant universe that we're talking about, however, is extremely far away. It's so far away that we're interested in studying things that are where the light in the visible spectrum has completely shifted entirely out of the visible wavelength, and it just keeps on going. In fact, even some of the ultraviolet has shifted all the way through the visible part of the spectrum and into the infrared. And so if we tried to image this in visible light, there would be a limit as to how far we can see, which is what Hubble faces, is a limit into how far it can see. The most distant galaxy ever detected by Hubble is a galaxy that we believe formed about 500 million years after the Big Bang. But we are confident that there should be things farther. We just can't see them with the Hubble. But we can see them with the Webb because of the infrared. So I have a brief comparison of different space telescopes that we have. You can see I've got the electromagnetic spectrum here, everything from really deadly gamma rays on the left of your screen to just ordinary radio waves that are harmless on the right side of your screen. And you can see a section in the middle where I have the visible light called out. And Hubble is operating in the visible part of the spectrum, a little bit into the UV and a little bit into the infrared, but not very far. Webb is principally in the near infrared and mid infrared. There's another telescope we have called Spitzer, which goes deep into the infrared. But we don't really need to go to the deep infrared to do what we want to do with the Webb Space Telescope. There's a second cool advantage to imaging in infrared. And here I have another image for you. This was a demonstration done at JPL and Caltech, where we have somebody demonstrating they've draped a ordinary plastic trash bag over their arms and hands, and they've taken an image of it with visible, but they also took another image in the infrared wavelength, sometimes also known as thermal imaging. And you can see in the thermal camera, to your surprise, that you can actually clearly see this person's arms and hands and fingers as though the trash bag is transparent. And so infrared wavelengths have the ability to see through things that visible can't see through. This lets us see into parts of the universe what's going on inside dust clouds in space that other telescopes can't see. And so that's another really cool reason why we image in the infrared.
It shows us what we can't normally see, so it becomes seen.
That's correct. Yep. And then we have to map that light into the visible spectrum so it looks like an ordinary picture to us, even though human eyes wouldn't see that at all.
Exactly.
Yep. Now, we also have the spectrographs, and they come up with, so I have a sample of a spectra here, so you can see what a spectra looks like. It's not a pretty picture, but basically different chemical elements and atoms give off light at very specific frequencies, and we can map those out, and we can essentially correlate those to specific types of atoms and specific types of molecules, and that's how we know what these clouds of dust and gas in space are made out of, or what atmospheres of exoplanets are made out of.
Okay.
I have one last image, and then we get to the pretty pictures. This one just talks about, we've got the beginning of the universe as we know it at the far right when the Big Bang occurs. Moving toward the left, that orange area here is an area where the universe was so hot that electrons couldn't bind to protons to form ordinary atoms. So the universe is essentially a plasma. The sun is a plasma. You can't see through plasma. It scatters light. So the universe wasn't transparent then. The universe does finally cool off. And then we get to this area that we call the dark age. The dark age is where we now have atoms, but the atoms haven't had time to get together to form stars. So we don't think there's any stars at that point. And then there's this purple line here that I'll draw. That purple line is when we think the first stars probably formed. And the Webb can see all the way back to that point. The Hubble cannot. The Hubble can only see to about, as I said, about 500 million years after things got going, but the Webb can see much farther. So that's the other reason why we wanted an infrared telescope, is we can go beyond and see light from the first stars. So this first image that I'm showing, this is actually the very first image reveal that we ever did with the Webb. I will show you some more recent images taken with the
It
Webb.
closely resembles the Hubble Ultra Deep.
It does. So this is sort of a deep field image. But there's some interesting things going on in this image. I'll go ahead and zoom in on it for you. And you can see, first of all, there's one of those diffraction spikes that I pointed out. So that's not in the distant universe. That's a star in our galaxy. But you can see these hazy, cloudy areas in the middle. And around it, notice there's these streaky things that sort of curve toward it. This is an object that has a lot of mass, and it has so much mass that it is curving space around it. And we get this effect that Einstein predicted called gravitational lensing. For funsies, it's a little bit technical. We shorthand call the image SMACS 0723, but in the lower right, it's actually called SMACS J0723.3 minus 7327. If you looked at the row below that, that's actually the coordinates for where the object is in the sky.
Oh, okay.
That's how we come up with these crazy names. So if you were wondering who came up with that name, so that's
Exactly.
why. There is an object in this, because it was the first image, we wanted to say, what's the farthest thing in the image? You wouldn't have just picked this up with your eye, but I'll go ahead and circle it. There's a little dot there, it's a little pixel. That is a galaxy detected by the Webb in this first image that is 13.1 billion light years away. Now that's not the most distant thing that the Webb has found. That was just the most distant thing in the first image. So this is kind of a significant image because when we did the image reveal, when Webb started doing science, this was image number 1. And so we wanted to call out this was the deepest thing we could find in image number 1. We do actually have a comparison in the mid-infrared as well, and you can see different colors. Red are galaxies that have a lot of dust in them. Blue are galaxies that don't have a lot of dust in them. Green are galaxies that have a lot of interesting chemical elements, organic elements in them as well. We'll talk a little bit about this concept called redshift, and if the audience is not familiar, you probably heard the term, but why do they call it redshift? So I'm going to show you why we call it redshift. So if I go into this image here, I'll call out some things. This is the same image that you just saw, and we've got 4 little call outs, and the top one, you can see what we're really interested in is the right side, this side over here, and you can see I've got a red spike, a blue spike, big gap, and then another red spike. And that tells us what elements we're detecting in that image. But if I go to the row below, you see the same pattern of the red spike, the blue spike, a gap, and then another red spike, except it slid to the right.
It's shifted.
It's shifted. And so this is actually a more distant object. So the one at the top was 11.3 billion light years away, but the row below is actually 12.6 billion light years away. So that shift tells us how far things are, and you can see the images below are even farther shifted to the right, so much so that they're cutting off. So that's what we mean when we talk about redshift. That'll come up from time to time. There's another thing that I can talk about, which is that not everything is shifted. So here are 2 galaxies called out in this particular image, but in this one, you can see that these 2 exactly match. And that means that these 2 galaxies that you see here, they're not 2 galaxies. This is actually 1 galaxy, and this is a concept called gravitational lensing, where the distortion causes it to appear like looking through a really bad piece of glass, causes us to have the illusion that there are actually 2, when in fact there's just 1. So that's the idea behind that. Do you want to see planet?
Let's take a quick look. I think we've got about a minute left.
If we have a second. Not everything turns into a pretty picture. So here's the idea is we've got an exoplanet. We've got a star in the background. That's the yellow thing. The black thing is the transiting planet. And you can see that the light curve dips. It gets dimmer when the planet passes in front. What we're interested in is to take the spectra of the star when there's no planet, then wait for the transit to occur and take the spectra again, and then compare the difference. And the difference will be that the planet has absorbed and scattered some of the spectra, and that tells us what elements are present in it. And so this was the first one that we did that with, and you can see that this planet actually has lots of water on it. Now, it's a very hot planet, so that water is going to be in the form of steam, essentially.
Vapor or gas.
Yes.
Exactly.
But that is, so not everything is a pretty picture.
But it helps us understand it quite a bit.
And that's the purpose.
There we go. Tim, I want to thank you for joining us with this discussion of the James Webb Telescope. The good news is, in the January program, we're going to continue this discussion with even more pretty pictures from the Webb. If you would like to visit our website, please do. The address is down at the bottom of your screen. And coming up to finish off this month's show is Stephen with What's Up in the Night Sky.
Thanks, Don. What's up in the night sky for December 2024? The solstice is on the 21st of September. So in the Northern Hemisphere, that's the mark of the start of the winter usually. And in the Southern Hemisphere, that's has to do with summer. The days change very slowly near the solstices and faster as we approach the equinoxes, and then slow down to the next solstice. December starts on day 1 with a new moon. There's also a new moon on the 30th, but nobody talks about a blue new moon, so that's not a thing. First quarter is on the 8th, full moon is on the 15th, and third quarter is on the 22nd of December. And then, of course, 30th is another new moon. Mercury is shown here on the 24th, and we're looking at approximately sunrise. Mercury is in Ophiuchus. It starts out the month setting an hour and a half before sunset to rising half an hour before sunrise. So it's after sunset to before sunrise. And it sets and then rises because we have inferior conjunction on the 5th of December. Mercury is probably better at the end of the month. Then we have Mars, Jupiter, and Uranus also shown here on the 1st and 2 hours before sunrise. Mars is in Cancer and rises in the evening, a few hours after sunset, 2 hours sooner, but still a little bit after sunset. And then we have Jupiter, Uranus, Neptune, Saturn, and Venus shown on the 31st, half an hour after sunset. Jupiter is in Taurus and has opposition on the 7th, so Jupiter is up all night. Uranus goes from Taurus to Aries and sets an hour before sunrise to 3 hours before sunrise. Neptune is in Pisces and sets 6 hours before sunrise to 8 hours before sunrise. Saturn is in Aquarius and sets 7 hours before sunrise to 9 hours before sunrise. And Venus goes from Sagittarius to Aquarius over the month and sets from 3 hours after sunset to 4 hours after sunset. Venus gets to do strange things. Venus is always great. It's a little better at the end of the month. And that's what's up in the night sky for December 2024. Remember, we don't charge money for this show, but we may tax your brain.